The question tells us we have 4 pairs of black socks, 3 pairs of gray socks, and 2 pairs of orange socks. Notice that the maximum number of socks we can remove without having a matching pair is 3. Once we select our 4th sock, we will be guaranteed to have a matching pair. So our answer here is A. Alright, our goal is to determine how many different passwords can be created using the letters in this word. Now to solve this question, we need to consider 3 cases. We need to look at 4-letter passwords, 5-letter passwords, and 6-letter passwords. Let's begin with 4-letter passwords. How many different 4-letter passwords are possible? Well, to solve this question, we're going to take the task of building 4-letter passwords and break it into stages. The first stage is selecting a letter for the first position, the second stage the second position, the third position, and the fourth position. Let's go to the first stage. In how many ways can we place a letter in this position? Well, there are 6 letters altogether, so we can accomplish this stage in 6 ways. Now, once we have placed one of our letters in this first position, only 5 letters remain. So there are 5 ways in which we can accomplish the second stage. Following along, there are 4 ways to accomplish the third stage and 3 ways to accomplish the last stage. At this point, we will apply the fundamental counting principle and find the product of these stages to get 360. So it is possible to create 360 different 4-letter passwords using these letters. Now on to the next case. We're going to take the task of building 5-letter passwords and break it into 5 stages. There are 6 ways to accomplish the first stage, then 5 ways, and so on. Once again, we apply the fundamental counting principle and find the product of these stages to get 720. So there are 720 different 5-letter passwords that can be created. When we apply the same steps to 6-letter passwords, we see that there are also 720 passwords possible. At this point, we want to find the total number of passwords. This will equal the following sum, which equals 1800. So our answer is 1800.
Certain school district has specified 5 different novels and 4 different nonfiction books from which teachers can choose to assemble a summer reading list. Each summer reading list must have exactly 3 novels and 2 nonfiction books. How many different reading lists are possible? Well, certainly the number of novels possible, the number of sets of 3 novels, that would be 5, choose 3. The number of possible nonfiction books would be 4, choose 2. And since any collection of novels can go with any collection of nonfiction books, all we'd have to do is multiply these 2 numbers. Now, we could use formulas to get them, but because we have to figure out 2 combinations at once, turns out that it's much, much easier to use Pascal's triangle in this calculation. So when we use Pascal's triangle, it's very handy just to memorize the 3rd row. So this is the row that would correspond to 3, choose something. Then we get the next row by just adding the 2 numbers diagonally. And then again, the 5th row. So this is the 4, choose something row. This is the 5, choose something row. We have to remember that the first place is the 0 place. 5, choose 0. And 4, choose 0. So we want 4, choose 2. Well, 4, choose 0, 4, choose 1, 4, choose 2 right here. 4, choose 2 is 6. We want 5, choose 3. 5, choose 0, 1, 2, 3. 5, choose 3 is 10. And then we just multiply those. 6 times 10 is 60. And so we select 60, answer choice B, as our answer.
We're going to take the task of creating possible 3-digit numbers and break it into 3 stages. Stage 1 will be to select a digit for the first position. In how many ways can we do this? Well, there are 10 digits in total. However, we are not permitted to use 0 in the first position. So we can choose from any of 9 digits. So the total number of ways to accomplish stage 1 is 9. On to stage 2. To select our digit for stage 2, we can select any of our 10 digits except for the digit we chose in position 1. So we actually have 9 ways in which to accomplish stage 2. And finally, to accomplish stage 3, we can choose from any of our 10 digits except for the 2 digits we chose for positions 1 and 2. So there are 8 ways to choose our last digit. The total number of ways in which to accomplish all three stages will be the product of these numbers, which is equal to 648, so our answer is B. Let's take the task of completing the entire test and break it into 8 stages. Stage 1 will be to answer the first question, Stage 2 will be to answer the second question, and so on. Let's begin with Stage 1. In how many ways can we answer the first question? Well, there are 5 answer choices, so we can complete Stage 1 in 5 ways. Now on to Stage 2. In how many ways can we answer the second question? Once again, we have 5 answer choices, so we can complete Stage 2 in 5 ways. Similarly, we can complete Stage 3 in 5 ways. In fact, every stage can be completed in 5 ways. The total number of ways to complete all 8 stages will be the product of these values. When we multiply these together, we get 5 to the power of 8, so our answer is C.
Let's have a look at this particularly tricky problem here. Let n equal 60 factorial plus 55 factorial plus 50 factorial. The unit digit of this number n and a number of digits to the left of the units digit are consecutive zeros before we come to the first non-zero digit. How many such consecutive zeros are there until the first non-zero digit? Just to review what factorials are about, that exclamation point there, what that's saying is multiply whatever number, so 60, by every integer down to 1. So for instance, if I had the number 4 factorial, what that's saying is take 4 times 3 times 2 times 1. So what this problem is asking us to do is add 3 huge numbers together. And how big are these numbers? Well, just to kind of give us an idea, let's start writing it out. 60 factorial is 60 times 59 times 58 all the way down to 1. 55 factorial means 55 times 54 times 53 all the way down to 1. And 50 factorial is 50 times 49 times 48 all the way down to 1. Now, I do know that all 3 of these numbers are going to end with a bunch of zeros. How do I know that? Well, look at this, right? 50 ends with a 0, and I'm going to multiply it by a bunch of other numbers. If I have a number that ends with 0, like 50 or 10, and I multiply it by another number, the resulting number will end in 0. And then I'm going to multiply it by 40 and 30 and 20, all the way down the line here, right? But not only the zeros, I also have 5s and 2s. So if I multiply a number that ends with 5 by a number that ends with 2, like 25 times 12, that is also going to create another 0 for this number. So let's just make this general and say that this is a huge number with a lot of zeros at the end. And this number, 55 times 54, has a few more multiples of 5 and 2, so it's going to be an even bigger number with more zeros. And finally, 60 times 59 times 58 is going to be the biggest number with the most zeros. So let's scale this down a little bit. Let's see what happens when we have a situation like, 1,000, 10,000, and 100,000. If we were to add those numbers together, what would we get? Well, we'd get 111,000. How many zeros does that resulting number have? Well, it has 3, the same amount as the smallest number here. And that is key, right? It's key to note that the smallest number, when we're adding these 0 numbers together, determines how many zeros the final sum has. So really, we just need to focus on this expression right here. We don't need to worry about these 2 bigger numbers. What I want to focus on is the number that has the least number of zeros. So what I'm really asking here is, how many zeros does this number have? The smallest number, 50 factorial. Well, to approach that, let's think of this. What makes a 0? So for instance, if I had the number, 4,000, each 0 represents a multiple of 10, right? It's 4 times 10 times 10 times 10. So I can say that there are 3 tens, essentially, that make up this number. But let's go even further. What makes a 10? Well, that results from multiplying a 2 by a 5. So every time I multiply a 2 and a 5 together, I get a 10. And therefore, a 0 is added to the number. So let's think of this. How many pairs of 2 and 5 are in this number here? If I broke every number in this list down to its primes and started pairing the 2s and 5s off, how many pairs could I make? Well, I could have a lot of 2s, right? This is a multiple of 2, and 48 is a multiple of 2, and 46 is a multiple of 2. I have more 2s than I know what to do with. So really the limiting factor here is 5. Every time I have a 5, I'll have a 2 to match it with, and that will give me a 10. So what are all the multiples of 5 in this list? Well, I've written them out right here. Here they are: 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. And let's see if we break these down into their primes, how many total 5s there are here. Well, 5 is just 5, right? 5 times 2, well, there's 1 5. 5 times 3, that's another 5. 5 times 4, that's another 5. 5 times 5, okay, I have to double count that one. That's 2 5s. 5 times 6, another one. 5 times 7, one more. Times 8, times 9, and 5 times 5 times 2, right? 50 is 25 times 2. So I have 2 5s in here, meaning that I have to count that twice. Let's count them up. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 5s that I can pull out of this number, which means I can match them with 12 2s, which will give me 12 zeros. The correct answer to this question is 12.